Okay, now I'm going to do a video for the elevator lab. This was a lab that basically we got on the elevator, rode it um, up, and then turned around and rode it down, all the while observing changes in the weight of an object that we placed on a scale. So for obvious reasons, I'm not going to video demo the actual lab, but I am going to discuss it in terms of the data sheet and the lab write-up that we did. So we started out with part one, where it asked you simply what was the reading on the scale. Now we used a 100 kilogram mass on a scale that read in grams, so we converted the reading on the scale to kilograms. So in kilograms, the reading on the scale that we got. So in grams, we got 99.8. We divided that by 100 to give us it in kilograms, and this, thus forth, is what we will do for each reading that was on the scale. Just keep that in mind as we move forward through this data sheet presentation here. So in this thing, it asked us to convert it into newtons. So to convert a mass into newtons, you have to multiply by acceleration. So this would be the mass times the acceleration, and this is our force, mg, our force, mass times gravity, better also known as the weight of the object. So thus forward, we're going to use that all the way throughout this lab. And then it asks us to create a free body diagram. A free body diagram, of course, is we're going to use the box for the object, and it just has arrows indicating the direction and the magnitude of the forces that are involved in this particular scenario. When we're in an elevator, we have the force of the gravity pulling it down, and then we have the force of tension, not normal, but force of tension holding the elevator up as a result of the cable that's hooked there. And so that's all we had to do. And in terms of objects that are at rest, like we were when we started this thing, we're at rest, the size of the arrows will be equal. So the size will be equal. And then moving forward, the arrow will change. The size of the arrow that is in the direction of the acceleration will always be larger than the size of the arrow that is in the other direction. So you'll just simply change the size of the arrow in terms of the direction of acceleration. So for part two, for example, now we have the size of the arrow here is larger than the size of the arrow down, and I have labeled these two separate ways so you can basically kind of see how we've added the tension to what I'm labeling as the normal force, but truly it's a tension force as well. But now the tension force is going to have to cancel out the gravitational force and create acceleration, so that's why it's larger. But in terms of what goes on the data sheet, it asks you for the reading. So the reading on the scale was this, divided it by 1,000, and got it into kilograms. And then it asks you to solve for the net force as well as the calculate the acceleration. So to solve for net force, we're going to have to take the force from part two that we just solved for, or we will solve for, and then we're dividing that or subtracting that from the force from part one, which is the gravitational force. So first of all, we're going to take and convert our grams into newtons by multiplying it by gravity, and so this becomes our force tension here for both of these. So that's this right here, and then net force equals the tension minus the mg, which we already calculated as 0.9, and that's, I think this is wrong here, it's not 0.09, it's just 0.979. So we're going to take and subtract 1.147 minus point, again point, or 0 point, whichever way you want to go, so the decimal's in the wrong spot there, 979, and we're going to get 0.1707. So this is correct. We just had the decimal misplaced there. And that is the net force. Now to get our acceleration, we're going to take net force divided by mass. So acceleration is going to be the 0.1707 divided by our mass, which we know from the first question. And this is going to give us our acceleration for step two. Step three, essentially, we are back at constant velocity. And constant velocity will look exactly like this in terms of the free body diagram. And so you will solve for You already know the net force of an object at constant velocity from your notes and from hopefully practice by now. You'll know the net force is going to be 0, and subsequently your acceleration is going to be 0. So in terms of calculating that, yes, sure, go ahead, calculate it if you want, but it's 0. So that moves us to steps 3 through 6, or 4 through 6 really, because you just did 3. And step 4 through 6, you are basically going to repeat the same exact process using these readings for the scale. This is what I got, so if you're not here to actually get the readings off of the scale, you can go ahead and feel free to use mine. I've converted these already into kilograms, so all you've got to do is essentially use this format right here and plug the new reading in right here, which of course will give you a new reading here, and then that reading will go there. This will be the same, then that'll change this, and then of course you plug that in there and that'll change that. And you'll just use this format for each of the additional parts. And then of course on your own you should be able to answer the questions in the conclusion without any problem. If you have problems with the questions, come and see me. But that is basically the lab.